So let's talk about what is known as a binary increment function. So what happens is that you have a binary counter which is initially will have all the values to be 0, and when I call this function once, then it should become 0, 0, 1. It should increment by 1. If I call this function again, then it should become it should increment the counter by 1, so it will become 0, 0, 1, 0. Again, if you call this, it becomes 0, 0, 1, 1, and if I call it again, it should become 0, 1, 0, 0. Basically you have to add 1 to this, right? So you next time it should become 1, 0, 1, 1, 0 and 0, 0. Now if I increment, then it will be 1, 0, 0. Finally, when all the 4 digits are 1, now if we increment it, all the 4 digits will become 0, and you'll have the 5th digit which is going to be 1, right? So our objective is to increment this, right? So we have an array, let's say that, which keeps track of this binary increment function. So when you call the increment function, so what you do is that if I start with the least significant bit, if it is 0, then you make it as 1, the algorithm terminates. If this was 1, then you go to the next bit and check whether that is 1. If that is also 1, make it as 0 and go to the next bit. So you start with the first location. As long as you see the 1, you have to flip everything and make it as 0. The moment you see the first 0, you stop there and make that to 1. That's precisely this simple code does. You have an array which is maintaining this increment function. So for I is equal to 0, as long as a of I is equal to 1, you flip all the bits to 0. And at the end of this, when you come out of this while loop, a of I is certainly going to be 0. I will flip back to 1, and then the algorithm stops. So if I do n such operations, so in worst case, what is the number of flips that you have to do? So what you notice is that if I do n and the nth operation is one of them, then what you have done is that you have flipped every bit in n. So the number of bits in n is log of n, and you have flipped every bit in n. So this last operation which is shown in the diagram, which is I had 1, 1, 1, 1, and if I call it as again, then it has to change to 1, 0, 0, 0, 0, 0. So in worst case, what may happen is that you may flip all the bits. So in worst case, the last operation is order n. So if I do n number of such increments, then it can be order n log n. So there is nothing wrong in saying that it is order n log n. So but it's we will show that this is going to be order n. More specifically, we'll show that the total number of flips that you are doing is not greater than 2n. So even though in one of the operations is too costly, where you are doing log n number of operations, some of the operations just one flip. If the first place itself is going to be 1 and you're going to change it to 0, then your algorithm stops there itself. Sorry, if you see a 0, then you just flip it to 1 and then your algorithm stops. So as long as you see once, you have to flip everything till you get a 0 and then change the 0 to 1 and stop. If I change a 1 to 0, in the next iteration, the number of flips that I'll be doing is just 1. So there are not too many operations which will take log of n, but in worst case, I may have to change flip log of n number of them. So before we coming to the amortized analysis, I want to quickly convince you that this will not take more than 2n. So if you observe the pattern here, so the first one is 0, now I flipped it, became 1, right? So next time it became 0, then again it became 1, and again it became 0, and so on, right? So in every iteration, so what you're going to see is that so you're going to change 1, 0 to the 1, 0 to 1, right? So there are flips that you're going to do. Flips could be of 2 times. You are changing 1 to 0 or 0 to 1. So the number of times you are going to change a 1 to 0 is a k. K is any number between 0 and log of n. But you are certainly changing 1, 0 to 1 and then stopping. Number of such flips where you change 0 to 1 is exactly equal to 1. But the number of flips of the kind 1 to 0, we don't know, right? So which can be a 0 or it can be a large number. In every iteration, you're going to do one flip of the type 0 to 1. But how many flips, how many ones you're going to change it to 0, we don't know, right? So that is where the problem is. So since I am doing n increments, there will be n number of flips which are going from 0 to 1. Now let's look at how many number of times 0 to 0 will be converted to 1, right? So if you look at the first bit here, every alternative, so if it is 0 changed to 1, and in the next iteration it's going to be 1 to 0, right? So I want to look at how many ones are going to be changed to 0. In the first iteration, if you change 0 to 1, in the next iteration you have to come back and change it to 1 to 0. So every alternative iteration, the most significant bit will be changed from 1 to 0. The same logic applies for the second bit. Instead of n by 2, it will be n by 4 number of times you are going to change it. So the total number of flips of the type 1 to 0 will be, in the most significant bit will be n by 2, in the next bit it will be n by 4, in the next bit will be n by 8 number of times. Every 4 times, once in 4 digits, you are going to change the second bit from 1 to 0, right? So we are not going to change the second bit more frequently, right? So the third bit is flipped only once in 8 times, and so on. So the total number of flips of the type 1 to 0, this summation is smaller than n. So the number of times you are going to change 0 to 1 is exactly equal to n, and 1 to 0 is also can be at most n. Intuitively, if you think at initially everything was 0, so every iteration I will change certainly 1 0 to 1, but I am saying that I don't know how many number of times I am going to flip 1 to 0, but the number of flips of the type 1 to 0 should always be smaller than the number of flips of the type 0 to 1, right? Because in every iteration I am only going to change 1 0 to 1, so the total number of flips of the type 0 to 1 is at most n. So the total number of flips of the type 0 to 1 also should be at most n. So the total number of flips will be number of flips of the type 0 to 1, which is exactly equal to n, and the number of flips of the type 1 to 0 can be at most n. So the total complexity of this algorithm is smaller than or equal to 2n. Let's analyze this using the potential function and the amortized cost that we defined. Let's define, so the idea here is that we want to define the potential function in such a way that when I do an easy operation is converting 0 to 1, right? Because the cost of that is 1, but here if the number of times the 1 is flipped to 0 is k, I don't know. So when I define a potential function, it should be in such a way that, so when I do an easy operation, the potential here can go up, but the potential when I do a costly operation should considerably decrease. It should decrease by a k if I am doing k such operations, right? So that so the amortized function will look like a neat function. Let's start with the potential function to be of the data structure now is the number of ones in the binary increment function. So initially I start with everything to be 0, the pi of d 0 is equal to 0, right? So now let's see each time when I do a flip, right? So when I do a flip of the type 0 to 1, so what is the amortized cost of it? If I change 1 to 0, let's say that I do k such flips, right? So this is k is the number of times this while loop is run. I don't know how many times this one is flipped to 0, but I know that exactly once I'm going to change 0 to 1 and our algorithm stops. Okay, so when I change 0 to 1, so the actual cost the number of flips that you're doing is 1, that is the actual cost of the operation, but you change 0 to 1, the change in potential is -1 because our potential function is, so the number of ones is increased by 1 because when you change 0 to 1, the number of ones in the sequence will increase by 1, right? So our potential function is defined as number of ones in the sequence. If you change 0 to 1, if you flip a 0 to 1, the number of ones will increase by 1. So the potential difference is +1. So the amortized cost of this operation is 2. So now let's pay our attention to what really happens when I flip a 1 to 0. If I flip a 1 to 0, let's say that if I do k such operations, let's focus on one such operation. If I flip a 1 to 0, the number of flips that I have done is 1, and the change in potential now is -1 because 1 is being changed to 0. So the number of ones in the sequence is reduced by 1. So the amortized cost of this operation is 1 plus minus 1, which is the change in potential is minus 1, so that it is 0. If I do k such operations, the actual number of flips that you are doing is k, but the change in potential is minus k, so the actual cost of the amortized cost of the operation is 0, right? So now if I do a flip of 1 to 0, the amortized cost is 0, and if I do a flip of 0 to 1, the amortized cost is 2. So yeah, if in the ith iteration, the actual amortized cost of the ith iteration is 2, because I don't care how many ones are flipped to 0, because the amortized cost of all such operation is 0. After that, I will do one flip, which is flipping a 0 to 1. So the amortized cost of each of this operation is 2. So I can easily write that sum of the amortized cost is smaller than or equal to 2n if I do this binary increment n number of times. But I know that this is a positive thing, so at any point of time the number of ones cannot be negative. So the sum of the actual cost, which is the sum of the actual cost, is smaller than or equal to sum of the amortized cost, which is exactly equal to 2n. So which will imply that sum of the actual cost that I am doing is smaller than or equal to 2n, right? So notice that it's very important to choose the potential function, so that when I choose an easy function, the potential increases by 1. So the number of ones in the potential function is now defined as number of ones. If I flip a 0 to 1, the potential increases by 1. The costly operation is I don't know how many number of times the while loop is run. That is the number of flips of the type 1 is flipped to 0, right? So every time when I do this operation, so when I flip a 1 to 0, the potential decreases, right? So when I do a costly operation, the potential is decreasing considerably, so that it can compensate for the costliness of the operation. So again, the important thing to note here is that so when I flip a 1 to 0, the potential decreased considerably. That is the number of times the while loop was running, so it compensated for this operation that we are doing. So at the same time, I am doing exactly one flip from 0 to 1, so the amortized cost increased by 1. So it is easy to, I don't know how many number of times the while loop was running. So but after I moved from the actual cost to the amortized cost, it doesn't matter, the cost of your amortized cost of each while loop is 0. So the only thing that matters is how many number of times you are changing your 0 to 1. So it is at most the total complexity of this algorithm is 2n. Now I want to compare this algorithm to the n additions, add operations that we did in the case of a binomial heap, right? So the binomial heap was empty, so it was number of elements was 0. Now I add the first element, so the number of elements becomes 1, right? That is 0, 0, 1. So now what really happens when I add the second element? There is a copy of b of 0, I again had a copy of b of 0, so I do one operation, right? So when I merge b of 0 with b of 0, it becomes b of 1, but there is no b of 1, so my algorithm stops. So there is a sequence of numbers. You're trying to add one more into the binomial sequence, binomial heap. So as long as there is a b of 0, you merge with b of 0, you get a copy of b of 2. If there is another copy of b of 2, you have to merge with this. If there is a copy of b of 3, you have to merge with this. Keep doing this till you see something which does not exist. If there are b of 8 which is not there, then you insert b of 8 and your algorithm stops. So what really happening is that it is exactly same as binary increment. There's already a number, you're trying to add one more number into the sequence, right? So the number of operations that you're doing is exactly equal to the number of flips done by this algorithm, right? So if I add nth number into the Fibonacci heap, the number of flip operations, number of merges that the binomial heap actually does is exactly equal to, in the binary increment function, how many flips you are doing. So there is always an analogy between n insertions that we are trying to do in the case of binomial heaps and the binary increment function, right? So every insert into the binary binomial heap is exactly same as one corresponding binary increment here, right? So the total number of operations done in the total number of merge operations done in the binomial heap is exactly equal to total number of flips that you're doing in the case of the binary increment function. So which is at most 2n, which implies that if you add n sequence of n numbers one by one into the binomial heap, the total number of merges that you're doing will not be more than 2 into n. So calling n insertions into the binomial heap is actually a linear time algorithm.